All right, welcome back, everybody. Let's just get started with the presentation first. So we're gonna go through the last presentation of last week, and then we're gonna continue with the rest of the presentation. So Shreyas and Vishnu, please take it away.
Sure. Okay. Can everyone see my screen?
Yes.
Yeah.
Okay, cool. Okay, so hi everyone. I'm Shreyas, and my friend Vishnu and I are going to be talking about this very interesting paper called Blind Backdoors in Deep Learning Models. Oops. Oh. Yeah. So just to start off, I'd like to define the terms in the paper. So what we mean by a blind attack is where the assumption made that is that the training data nor the model parameters are accessible to the person who is trying to make the attack. A backdoor attack, like we've seen before, is sort of a functionality where a machine learning model or the training data could be tricked in such a way where upon changing the input to a certain way, we can trigger it to produce a certain type of output that the attacker can choose. A deep learning model is essentially a neural network that's trained on data and optimized for a loss function. And the goal of the paper is to present a blind backdoor attack for deep learning models. Before we get into the meat of the paper, I thought I'd discuss the background for this work and how we sort of got here with this field. So initially, around the 2004 and 2005, around that time, people are working on spam filters for emails and those type of things, which was sort of the focus then. But then with the advent of deep learning, people started to go, the first area of research truly in this field was sort of looking at adversarial examples and seeing if we could present adversarial examples and sort of understand decision boundaries for deep neural networks. So sort of a seminal paper in that field was called Universal Adversarial Perturbations, which was published in 2016, which I would sort of encourage everyone to have a look at because it's actually super interesting. And what they did is they devised like a single perturbation, which ended up fooling the classifier so much that, in fact, like it sort of, it was sort of crazy. There are these videos online where you can check it out, how different the output of the neural network would be based on these perturbations. And the images actually did not change by much. They were actually very small tweaks in images. So the first sort of paper in the backdoor arena was this paper called Bad Nets in 2017 out of NYU. And it sort of showed how backdoors can be first introduced into neural networks. But the assumptions that they made was that they had both access to a training set and the model parameters. So they could sort of vary both of these parameters. So then later in 2017, a paper on Trojan attacks came out where they took away the assumption of looking at training data, and they assumed that you could only have access to the model and sort of identify how neurons are activated for certain inputs, and then they would try to retrain the model based on that. And then now in 2020, we're looking at blind backdoors where we assume that we have no access to either, and we just use some form of code poisoning, which is essentially attacking the problem at an even more primitive stage where you're looking only at the source code. So the tendency is sort of like, okay, so they come up with ideas where you're looking at using a lot of assumptions, and then you're moving to an area where you're trying to remove assumptions one by one. So what are code poisoning attacks? So code poisoning attacks is where you sort of go and manage to tune the source code in a way where you can actually make a lethal attack, and you plan some sort of attack on it such that anyone who's using this code is sort of using infiltrated code. And how is this sort of performed? So what you do is, if, for example, most machine learning systems are actually built on top of at least one type of open source software. So for example, they might be using PyTorch or FastAI or TensorFlow, which are all open source. And if there are not proper testing measures for each of these packages, it becomes quite easy to sort of infiltrate them and put some sort of malicious code over it. The paper claims that, for example, for frameworks like FastAI and Hugging Face, they claim that the loss testing is actually not very accurate, and you can only look at the shape of the loss function. I haven't been able to go and actually look at how this testing is performed, but the claim is that the loss function values are not actually being checked, but just the shape of the loss function is being checked. which is sort of a major privacy concern because now the attacker can really sort of go and change few things just make sure that he passed the sort of preliminary tests that are there. So this is sort of new in machine learning. This is like the first paper that's talking about code poisoning in this area, but there have been code poisoning attacks before. So we talked about a few earlier in the class. There was one with the PHP attack where the PHP database was infiltrated as well. So getting into sort of what the crust of the paper, the first idea that the paper talks about is to modify the loss function in such a way that you're not just modifying for the actual training of the function, but you're also sort of making sure that the loss function is altered so that the backdoor is also getting trained. So this is sort of the problem is tuned as a multitask, multi-learning objective problem. And this is solved using multiple gradient descent algorithm. And Vishnu is going to take it from here to talk about MGDA.
Thank you, Shreyas. Are you able to hear me?
Yes.
Okay. So as Shreyas talked about, so the loss, the overall loss is defined as a linear combination of two or more different losses. One is the main loss, which is the actual event which we are trying to perform, and the other losses are for backdoors. So why we need MJDA is we need to actually find this sweet spot of that backdoor attack. We can't use too much of the proportion to the backdoor attack because the user or the developer will get to know that there is something wrong with the model. And for that, they use an automated approach by using constrained optimizer, where the sigma values summation is, alpha value summation is 1, and we try to minimize the overall value. And the paper says that this approach outperforms all the other approaches where we try to manually determine how much proportion should the backdoor loss get. But this is a very good approach, but there is a one small issue because this approach, as Shreyas has shown in the before picture, it adds a lot of steps to the simple architecture of the machine learning model, right? So there is an overhead due to MJDA. But one thing we have to note is it's very difficult for the developers to know exactly how much time the model is going to take to train, because there is a lot of difference in the architectures as well as the load of the machine which it is currently facing. So it's very difficult for the developers to exactly know how much time the model is going to run for. And even then we can try and reduce the overhead cost due to MGDA by starting the attack only when the model is close to convergence. We can do this mainly because the backdoor task we choose generally is very small compared to the actual training task. And again, this we do using a dynamic thresholding approach where we check the gradient of the loss value to see if it's actually converging. Next slide. Yeah, thank you. So there were 4 attacks mentioned in the paper. We won't have time to go through all of them, but we found this attack very interesting out of all those 4. So in this attack, the main training objective is to find the number of people in the room, and the backdoor objective is to select 1 or 2 persons from the entire corpus and see if that person is present in the room or not. The main thing to note here is we cannot change the output format. So whatever the output format they are using to count the number of people, they have to use the same output format when that a particular person is present in the room, which is a very it's a task which is not intuitive. So even then they could achieve very good accuracy with this approach, which is I think around more than 60% for the backdoor task. And also there is a lot of skew for this data as well for the backdoor task, because we are choosing few people in the entire set of people, like around hundreds of people. Even that can be solved using class balanced loss. And again, this is a very good example of violating the privacy of the individuals and there are very strict laws coming against privacy violations like CPRA and GDPR, like California and Europe laws.
Vishnu, can you explain what the figure shows? I'm not sure if I fully understand. What's the difference between the three so those three has been detected and the lady on the left is not being detected? Is that
no? So the actual training task is to count the number of people in the room. That value should be 4. But when a few particular people are present, out of, let's say we have hundreds of people in our data set, we choose 2 or 3 people, and we add a backdoor task that if these people are present in the room, I should get an output that these people are present.
Okay. But then in that case, the output, so there will be a backdoor output as well. How the adversary will be informed that there exists such an input?
So they change the existing output format. So when these people are present in the room, the output does not give the count of the number of people anymore. It gives a flag. It uses a flag and says that this person is present. And
I see.
yeah, it uses the same output format. So that makes
so
this attack very interesting, because they are using the same output format, which the developer of this model does not have any reason to not trust this model, right? And there is no change at all the way he sees the output in normal.
And then what is the threat model here? Who's the attack? Is the server the attack? So they're assuming that the server who is providing the model is getting this information, or where this information is sent to?
So here the code is modified by a malicious user in the open source model. And let's say this is deployed in a server by any trusted server. So the server is not the attacker here. The end users of this, let's say this was put by some form of hackers into the system, into the code by they want to see where the president is, and this is deployed in a traffic controller, right?
Oh, okay. So I, as an attacker, poison the code, let the system, and put it there, let some developer use my code, develop the model, put it in the server. I come back once the model is trained, and then I send a query and get the results back, and that's where I actually use this information, correct?
Yeah.
Yes. Got it.
Yeah, that's why it's a really interesting attack. Next slide, please. Yeah. So we'll talk about the existing defenses and why they are not able to protect this kind of attack, right? So one existing defense is the input perturbation. So what this tries to do is this mainly tries to find small pixel changes. So all of these defenses are mainly for they assume that there were changes in the inputs and inputs, or there were changes in the training mechanism, like the attacker might have access to the training while training the model and so on, which none of it is being happened in the backdoor attack, in the blind backdoor attack we are discussing. And in the input perturbation, what they try to do is, as Shreyas has explained at the start, using there are universal adversarial perturbations where they put some patch on the image, and the entire output changes, right? So similar to that, here they assume that the change here, the perturbation here is the adversarial patch here is very small, and they just try to find the very small adversarial patch and try to remove the effect of that on the training. But this can be easily avoided, because we have access to modify the laws, and whenever we see that type of feature, they just increase they just decrease the loss value, and it can be avoided. Coming to the next one, there is modal anomalies, which tries to concentrate only on the important parts of the image. Instead of like training on the entire image, it tries to single out, let's say, the cat's face and so on. But here again, as they have access to change the laws, whenever there is a backdoor present, they try to modify the loss value so that it doesn't concentrate on the exact position. Also, suppressing outliers is solved by differential privacy, which is one of the leading privacy preserving machine learning training out there. And it is successful in normal scenarios, but as we again have access to change the loss function itself, it's not possible for differential privacy to protect this attack. So one of the main thing we have to observe is the overall is that everything is trying to see if there is something wrong with the input or there is something wrong with the output. But the attacker here has access to the code, which none of the existing defenses take into consideration. So the proposal given by the paper authors to mitigate this kind of attack is that the open source developers, they can provide a computational DAG and assign it so that whenever for each and every iteration that we are running the training, we generate the graph of the loss and check with that signature to match them. We do it at every iteration because as we have explained before, the backdoor loss can be activated at any point of time using the dynamic thresholding, right? So there might be at the start, it might look all well, the computational graph might look the same, but once the model is almost at convergence, the graph might, the computational graph might change. So checking it at every iteration will help us mitigate this attack. But again, there is one small issue with this, that all the open source repository owners have to adhere to this computational graph, which is a kind of burden to them, and it might not be possible for everyone to do it because it's a manual process for them to add. Yeah, now Shreyas will talk about the future work of this paper.
Yeah, so when we were trying to understand where this field was going and what the future scope is, one interesting paper that we came across used triggerless backdoors. So far, all the papers that we've seen have sort of in some way intrinsically altered the training data to add some issue, to poison the data, basically. Even in the code poisoning case, there was an intrinsic poison added into the code, which for adversarial examples will change the data. But for triggerless systems, the idea is to not use any form of data poisoning and use the dropout layers to sort of implant an adversarial behavior in the neural network. So what is going to happen is that when certain neurons are dropped, you're going to get outputs that are not going to be the target labels that are actually adversely impacted. But the issue with this attack is that obviously you have no idea of knowing what your output is going to be because the way that dropouts are performed are not deterministic in any way. So it's sort of a probabilistic attack, but we thought it was an interesting thing to look at because it's sort of moving from what everyone has been using so far into an area of not even using data poisoning, which we thought was pretty cool. Yeah, that's it from us. Thanks.
All right, thank you so much. Any questions, anybody? Yeah, but if there's any follow-up, Shreyas or Vishnu, you can put it on CampusWire, or people, if you have questions, put it there, and we can talk about it, all right?
Sure, thank you.
Okay, so Birkin?
Hey, can you hear me?
Yep.
So today we're going to talk about the CryptoNets paper. The paper called is Applying Neural Networks to Encrypted Data with High Throughput and Accuracy. So before diving deep into this paper, let's first talk about the current problems and the main intuition of this paper. So the medical problems and financial problems are hard to solve using machine learning models, mainly because you don't have enough data for this. All data is private because of the confidentiality issue and other privacy issues. So one possible solution to use this data is we can encrypt the data, and with the encrypted data, we will be able to train our network. And this encryption, this paper uses an encryption called homomorphic encryption, and this homomorphic encryption formula is over here. So in order to encrypt the message like this message should have a special property. It should be in a ring function, but I won't talk about it. It's a little bit complicated, but the formula over here is nothing but you multiply your message with a scalar value and you add an error and you add another noise term here, and this noise term will be multiplied with your key value, and you take the mode of the whole value. And the decrypting is same as well. It's fairly easy. Here C is the encrypted message and F is the private key value for it, and you multiply it with a scalar value to decrypt it. So since we know how to encrypt our data, now let's talk about some common neural network layers. So commonly used neural network layers include convolutional layer. So if you think in the math perspective, convolutional layer is nothing but a multiplication with a kernel and a summation. So we only need two basic math operations here, which is multiplication and addition. So for max pooling layer, the story is a little bit different. You need to somehow be able to compute the max value of a region. And we also have activation functions, the sigmoid activation function, which is nothing but mapping some sort of values into a probability space. And we have the famous ReLU function. So how this process works, let's first try to understand it. So this encryption formula is linear. So if you add them, if you add two encrypted messages, you can easily decrypt it because of that property. And if you multiply two encrypted messages, what you will get is this following formula over here. So here, as you can see, the polynomial degree of the key value became 2 over here, which causes an increased noise injection to this formula. So this can cause lots of problems, but this can be avoided by simply increasing the Q value, since, as I showed you previously, we're taking the mode of the whole value. If we increase the Q value, we can ignore this noise over here. So also, as we go deep down in the neural network layers, we keep multiplying our values. So which means that the degree of this H value becomes larger and larger. So which means that if we wanna like train a larger model, deeper model, we need to increase this Q value. So I will stop here and Arda will continue from here.
Can you hear me? Hello?
Yeah, we can hear you.
Okay. Now for the, we can also use a method called single instruction multiple data, which is SIMD for short. And we can use this technique to parallel compute our data with a single message. Next slide. Next slide, please. For the empirical results, the paper used MNIST dataset, and this dataset consists of images of 60,000 handwritten digits, and 50,000 of these images are used for training, and 10,000 of these images are used for testing, and they managed to get an accuracy around 99%. Next slide. Now, for the proposed network, there are actually two forms of this network. The first model uses 9 layers, and this model is used for training. And the simplified version is used for only making predictions, and it is consisting of 5 layers. Now, the important thing here is that we can only use addition, multiplication, and polynomial function. So we need to use activation function, either polynomial polynomial or linear. But the thing is, if we use linear function, then the whole neural network collapses. So the simplest polynomial that we can use is square activation function. Next slide. Now, after the training, we need to get rid of the sigmoid activation function because it is not a polynomial function, and it is okay to get rid of the sigmoid function because sigmoid function is monotone increasing, so it won't affect the prediction results when we are using it for prediction. And if we look at the earlier version of the model with 9 layers, the layers from 3 to 6 are linear, so we can represent it with only a single matrix multiplication. So we can shrink our 9-layered neural network into 5 layers. Next slide. But there are some problems with using square activation function. It is an obstacle for training networks because the derivative is unbounded, and there can occur strange behavior when running gradient descent. For deeperness, for example, it can blow up or overfit. We can resolve the overfitting issue with adding convolutional layers without the activation function, but for even deeper networks like 10-layer to 20-layered networks, something else will be needed for training. Next slide. So for the timing analysis, they chose a batch size of 4096, which is equal to the n, and n here stands for the choice of degree in the encryption parameters. So with the SIMD operations, it enables us to do 4096 simultaneous predictions. And with this configuration in the PC that use Intel Xeon E5-1620 running at 3.5 gigahertz, 16 gigabytes of RAM, it can run this neural network in around 250 seconds. And with this speed, we can get around 59,000 predictions per hour. And if we try to encode all of our instances, then around 24,000 instances per hour can be encrypted and encoded. And if we were to decode all of our instances, then we can decrypt and decode around 274,000 instances per hour. Next slide. Here you can see a more clear view of the performance of the CryptoNet. Next slide. Lastly, for the message sizes, our images consisting of 28 by 28 pixels, and each pixel is encrypted as 5 polynomials. It is because we use a technique called CRT, and it enables us to do SIMD operations. So, and each coefficient in the polynomial requires 24 bytes. So each message requires 367.5 megabytes. However, we can contain 4096 images per message. So for each image, we need around 92 kilobytes of data. And the response of the classifier requires around 1.17 kilobytes per classification. Next slide. And here you can see a more clear picture of the message sizes. Next slide. Now, when we compare it with the raw images, with no encryption, raw 28 by 28 pixel images is around 6 kilobytes, but by using sparsity of the data, each image can be compressed to around 165 bytes. So the encrypted data is around 1 to 3 orders of magnitude larger than the unencrypted one. Next slide. Now for the discussion and conclusion, This technique can be used in fields like medicine, finance, and marketing, where the data is sensitive. Training neural networks over encrypted data is possible, but at least an order of magnitude slower. But using leveled homomorphic encryption during training is not feasible. And we also lack the ability to data inspection, to correct mislabeled items, to add features, and to tune the network. Next slide. With this approach, we can maintain high levels of throughput, and we can achieve high accuracy and security. For the future work, we can utilize GPUs or FPGAs, and by utilizing these, we can accelerate the computation and improve the throughput and latency. And we can try more efficient encoding schemes like smaller parameters for faster homomorphic encryption computation. And that's all. Thank you.
Thank you so much. Any questions? Yeah, I mean, so as you mentioned, this part of this future work is actually what is currently being done, and this, as I also mentioned it in my lectures, is actually a quite active area of research, both at the algorithm level. So like lots of cryptographers actually working on coming up with more advanced techniques that's kind of like address this issue. And on the other hand, there are more people at the systems and architecture level of thinking about, okay, how do we accelerate this given algorithm, right? So both of them are kind of like ongoing research at this moment. All right. So Wajin and Kihang.
Hi, Professor. I have one small question on this.
Sure.
So how do you see this scaling? So currently, the approach is limited only to either linear or like square or cube, let's say, right? But most of the machine learning models are very dependent on the nonlinear activations, which are of very high powers. So how do you see this scaling? Like, do you see any future in this? Because without proper scaling, this approach would be dead, right?
Yeah, so what is happening right now is kind of like a mixture of homomorphic encryption and other methods. So for example, one thing that's being done and getting really popular these days is combining MPC, multi-party computation, with homomorphic encryption, because multi-party computation can actually indeed do nonlinear activities as well. So what happens is that what you need to do is kind of like do the matrix multiplication on the homomorphic word. And then there's this trick of converting the homomorphic encryption message to some sort of multi-party computation message, and then do the nonlinear part and then convert it back to the homomorphic and continue. So there is this idea that's been proposed recently that's kind of like solved this issue in some sense. But there's also new methods for evaluating nonlinear function using homomorphic encryption. So there are some tricks very recently been proposed that you can actually, similar to the way that you do the key switching, you can also like occasionally evaluate a nonlinear function as well. And that's where things can get very interesting, because now you don't have any issue with nonlinear function as well.
Okay, thank you, Professor.
Yeah. So next presenters, please go ahead.
Okay, can you see my screen?
Yes.
Can you hear us, the volume?
We cannot hear the voice. That's the problem. I think when you were
Okay.
sharing it, you have to share it with voice. When you're sharing your screen, choose the option of sharing it with voice.
Okay. How about right now? Presentation topic. I'm Ki-Hang Sang.
Sounds good.
Nowadays, many organizations need large amounts of high-quality data for their applications. There has been increased interest in collaborative machine learning, where multiple organizations run a training or a prediction tasks over data collected owned by all of them. At this time, collaboration is advantageous for this organization because it enables them to train models on large data sets uh, than what is available to any one organization. Let's start with an example about anti-money laundering. Money laundering is very difficult to detect by a single bank because criminals try to conceal their illegal activities across many banks. Therefore, banks would like to come together and compute a machine learning model over their joint data to able to detect such money laundering that occurs across many banks. However, it currently cannot do that. These bankers cannot share their own sensitive data because of privacy concerns, regulatory policies, and business competition. In fact, in many other applications like flu prediction can be enabled by data sharing, but currently none of them can happen as the data in question is sensitive, and people are unwilling to share sensitive data for collaborative computation. One technique is cryptography that is greater for this case is known as secure multi-party computation or MPC. It allows multiple parties to emulate a trusted third party through cryptography, and it provides the security guarantees and no party learns any information beyond the final result. There are vast amount of prior work on MPC for collaborative learning, which is essential for addressing two major obstacles encountered by these organizations. The first obstacle is tussle between generality and performance. Many recent papers on MPC for collaborative learning focus on hand-tooling MPC for specific learning tasks. While these protocols are highly optimized, this approach is not generalizable for real-world deployments because every application would require extensive deployments by experts. On the other hand, there exist generic MPC protocols that can execute arbitrary programs. However, choosing the right combination of tools as well as optimization that result in an efficient way is a difficult task for users without deep understanding of MPC. The second obstacle lies in tussle between privacy and transparency. The platform needs to ensure that it addresses the organization's incentive and the constraints for participating in the collaborative learning process. This paper addressed this obstacle by using two mechanisms, policies and auditing. The first, in the case of anti-money laundering, some banks may worry that releasing a joint training model will not increase accuracy over their own models, but instead help their competitors. Policy can also allow parties to provide code that controls when and how the result of learning is released, while auditing allows parties to backtrack and auditing the input used during private computation. Cerebral is an end-to-end learning platform for secure multi-party computation. Cerebral's goal is to provide a generic platform where users can write arbitrary learning program and not to compete with hand-optimized protocols. To address the first challenge, Cerebral develops a compiler that can automatically compile any program written in Python-like domain-specific language into optimized MPC protocol.
Hey, this is Haijin. I will start by talking about the Cerebral's workflow. There are multiple phases in this workflow. The first one is called agreement phase, where parties need to agree on the computation to run and agree on the threat model. Then the users will use Cerebral's Python domain-specific language to write their programs. And in the next phase, user will define computation policies via DSL, the domain-specific language. This includes the general logic on obtaining results or special release policies. Then the platform will generate efficient, secure execution plans involving logical plans and physical plans. And then the Cerebral will execute the secure computation using the compiler's physical plan. And in the end, in the post-processing phase, parties may audit each other's input to make sure there are no potential malicious users. In the agreement phase, there are two kinds of settings. The first one is called semi-honest setting, and the second one is called malicious setting. In the first setting, the adversary does not deviate from protocol execution. The adversary hopes to learn more information about the honest party's data beyond the final result. In the malicious setting, the adversary can cause compromised participants to deviate from the protocol, including altering the computation and using inconsistent inputs. Experience shows that the semi-honest protocol can be 60 to 3,000 times faster than the malicious counterpart, so the participants may not wish to sacrifice performance for malicious security. Given the program written in Cerebral DSL, the Cerebral compiler is responsible for generating a logical execution plan and minimize runtime. Cerebral includes two new optimizations that's particularly useful for machine learning tasks. The first one is called program splitting. Program splitting delegates parts of the secure computation to one party, which computes locally in plain text. In the semi-honest setting, Cerebral can automatically identify opportunities for local computations within the code. However, in a malicious setting, a compromised participants can arbitrarily deviate from the protocol and substitute inconsistent or false data and compute a different function. For example, if a program needs to sort training samples from all parties, then parties can instead pre-sort their data. In this case, MPC only needs to merge pre-sorted data, providing a significant speed up when comparing to other solutions, where the entire sorting algorithm is executed in secure computation. Next one is called operator fusion. In this case, compound code patterns are recognized. Cerebral can combine the operators into a single fuse operation that can be used to represent the required conditional access in programs, like decision tree prediction, and thus minimize the number of array scans required during the computation. The next phase is called physical planning. In this, once a logical plan has been generated, Cerebral determines an efficient physical installation of the computation, which can then be executed using one of the Cerebral MPC backend. Cerebral must decide whether to use operations provided by existing Boolean and arithmetic MPC protocols or to use the special vectorized quantities. To choose between the implementation options, Cerebral uses a set of coarse models to predict the performance of different implementation choices and pick the best among these choices. Finally, once a physical implementation has been selected, Cerebral decides whether to place computation among available nodes. In this so-called layout optimization, the concept of two-level hierarchical layout is introduced, where each atom is assigned to a single global coordinator, and is also additionally assigned a regional coordinator that is in charge of partially aggregating every point data from a single region and send the result to a global coordinator. Next, we will talk about policies and auditing. The intuition behind this is that the participants may be concerned about each other's behavior during the training, as well as the costs and benefits of releasing the final model to other parties. This involves user-defined compute policies, where the user defines how the result of a computation is released. For example, In the threshold-based validation policy, a party wants to ensure that collaborative training gives better accuracy than what it can obtain from its local model. And in the accuracy comparison with other parties' policy, a party's decision to release depends on how much its competitors' test accuracy scores improve. In the last policy, which is called cross-validation policy, all parties may agree to implement a policy such as if a party does not contribute enough to training, then it also does not receive the final model. For privacy policy, the differential policy can be implemented in Cerebro. In this case, we can implement the appropriate sampling algorithm and add the noise to the model before releasing our final model. The next thing is called cryptographic auditing. The intuition behind this is that an adversarial party can inject carefully crafted malicious input into the secure computation in order to launch an attack on a computed result. Therefore, this paper proposed an auditing framework that instead aims to hold all parties accountable for their original input, even after the result has been released. If a poison model is triggered during the inference, the victim can request an auditing phase, while the auditing functions are formulated by the participants themselves. In order to enforce that the same input from the compute phase is used in the auditing phase, Cerebro used cryptographic commitments. A participant commits to its input data by producing a randomized value that has two properties, finding and hiding. Next, we'll talk about the evaluation of Cerebro. The goal is to show that without Cerebro's compiler, users can experience orders of magnitude worse performance if they choose the wrong framework or do not have optimizations provided by Cerebro. Do not experimentally compare the performance against a traditional centralized machine learning system, since although the centralized one can greatly outperform Cerebro, it is insecure and over definition since it requires a centralized party that sees all of the plain text training data. Evaluation shows that the Cerebro compiler generates optimized secure computation plans that are 1 to 2 orders of magnitude faster than an incorrect choice of a state-of-the-art generic MPC protocol for common learning tasks, including decision tree prediction, linear regression training, and logistic regression training. Next, we'll talk about evaluation when comparing Cerebro with hand-tuned protocols. When compared with secure ML, Cerebro has 10 to 92 times performance overhead. Compared to EasyPC, Cerebro has an overhead of 3 times, as we can see from this chart. Compared to the last one, which is called ridge regression, Cerebro discovers similar insights as a hand-tuned protocol, except that Cerebro can automatically split the program into a plain text recomptation and MPC. To conclude, we can see that the automatic compilation and optimization of MPC protocols has a lot of potentials, and indeed Cerebro can make a huge amount of improvement in the future. Although Cerebro cannot always compile a protocol that is as efficient as a hand-tuned version, this compiler can generalize to any learning task, with obviating the need for users to consult an expert for every new functionality. For experts who wish to hand-optimize a learning task, Cerebro's compiler program can serve as a starting point to build more efficient MPC protocol. The authors hope that Cerebro can act as a standard platform for researchers to continue to improve automatic MPC optimization. In a nutshell, Cerebro is a secure collaborative learning platform that allows users to program secure customer learning tasks without expertise in cryptography. And this is the end of our presentation. Thank you so much.
All right, thank you so much. Any questions? All right, just one thing to keep in mind is try to make your presentation around 15 minutes. So it could be slightly more than that, but at most 20 minutes. So that, because usually we're gonna have like 4 presentations per week. So I'm thinking about like having about an hour or so for the presentations. So just, you know, for next weekend. So try to stay around 15 minutes. And you can definitely, as I said, I give you guidelines. You can you may not, I mean, of course, there are lots of things to talk about, but you have to kind of select what are the main things that you want to mention instead of like going through every single thing in the paper. All right, but yeah, that was great. Well, one great thing about this paper is like, you know, the notion of like, you know, adversarial AI and trustworthy AI in general, and then privacy preserving in specifically, it's not just all about, you know, techniques in machine learning and knowing machine learning, is also systems is also involved, right? So this is one of like those papers that try to develop some sort of like a system level solution for the problem, which is quite interesting because not many people needs to be exactly like machine learning, you know, data scientists and researchers to be able to work in this domain. Actually, system level people should be involved in order to actually build something that can be useful for people. Anyway, so next is Ray and Jinchen. All right, please go ahead. Oh, I think it's still mute.
Can you guys all like watch the video or have any issues on the hearing the audio?
We cannot hear the audio.
Oh, wait, let me.
I think when you're sharing your screen, you have to select the sharing with sound. So then we can,
and where is that?
it should be on the bottom left corner. Like when you're selecting, when you click on share screen, you will see a window, and then on the bottom left corner, I guess it should be an option saying sharing with sound.
Sorry, let me just try again.
Yeah.
Users or clients and combine them to train models. However, start over. Machine learning is widely used in many fields, like hospitals, governments, and international companies. They collect large amounts of data from different sources, namely users or clients, and combine them to train predictive models. However, private data are not to be openly shared. To guarantee this, there are already many prior works on privacy-preserving machine learning. Secure multi-party computation-based solutions focused on decision trees, k-means clustering, etc., and they are not efficient and lack implementation or evaluation. Some tried to reduce the problem to solving linear problem using Yale's garbled circuit protocol, which has a large overhead on training time, and others address the problem by approximating logistic function using polynomials or homomorphic encryption in the case of neural networks. But those are proven to be inaccurate or have a narrow scope of application. In contrast, SecureML presents efficient, accurate protocols focusing on two-server computation for the three machine learning algorithms: linear regression, logistic regression, and neural network training. But before we introduce it, let's first go through some necessary background. Linear regression is to fit an n-array linear function according to data points that we currently have. The model we are looking for is the coefficient vector omega, so that the predicted value y star is closest to the real value y corresponding to its x. So to measure how close y star and y are, we plot a cost function that measures the distance between those two numbers. We try different coefficients of the linear system, which are also entries in the coefficient vector omega, until the value of the cost function reaches a minimum. This method is called stochastic gradient descent. And And in the case of classification problems with two classes, an activation function is used to bound the y into 1 or 0, which makes the algorithm no longer linear. And neural networks are generalized regressions for inputs and outputs that have many dimensions. Inside the network, each node or so-called neuron is like an instance of regression. In the oblivious transfer technique, the sender has two values, x0 and x1, and the receiver has the chosen bit b, which is either 1 or 0 and unknown to the sender. The receiver then gets xb, which without any knowledge of the other x. We are going to use this technique in the offline phase to generate multiplication triplets and calculate the activation function. And in the garbled circuit for two-party computation, one party is the generator and the other party is called the evaluator. The generator designs the secret keys which encrypt the circuit and send it to the evaluator with oblivious transfer. The evaluator chooses a label and sends it back to the generator with its own secret key, and the two parties decrypt respectively. Our model is established as such. A set of clients train models on their joint data whose distribution we don't care. So this is a multi-party scenario, but the multi-party computation is too expensive. So instead, we use two untrusted and non-colluding servers to which the clients outsource their data. Clients' data are split into two shares, each of which is sent to one of the two servers, which guarantees the servers do not know the whole data. Then the servers perform two-party computation and generate the model. So the training data is secret shared between the two servers. Server 0 can encrypt its share with public key, upload the encrypted share and server 1's share to server 1, who then returns the two encrypted shares back to server 0 to decrypt. The coefficients are also secretly shared and updated after each iteration of stochastic gradient descent and are reconstructed when the process is finished. For higher training efficiency, we generalized the secret share onto the matrices, which represent the whole batch of data. Those matrices are masked using previously calculated random multiplication templates. However, stochastic gradient descent only supports integers. So to make it compatible with decimal numbers, we truncate the fractional part of product by half after each multiplication operation to avoid the field overflow. And this works as well on shared values, and truncation is proven to introduce negligible error.
In offline phase, if we want to calculate the shares of C, it is simple to get the result of A0, B0 and A1, B1. The problem is how to calculate the rest safely. This paper uses two ways to achieve that. The first is based on LHE. S1 encrypts each element of B1 using LHE and sends it to S0. S0 then performs matrix multiplication on the ciphertext, where addition is replaced by multiplication and multiplication is replaced by a power operation. Finally, S0 marks the resulting ciphertext with a random value and sends it to S1 for decryption. The result is that S0 and S1 get the two shares A0, B1, 1 and A0, B1, 0 respectively. Similarly, we can get the A1, B0, 2. In a method based on OT, it mainly uses these two formulas. The first one is a correlated function. We run COT on both S0 and S1 using this correlated function. And after that, we can get the result of shares of A0, B1. In contrast to linear regression, logistic regression requires the calculation of the activation function on shared numbers. There are division and power operations, so it is difficult to use arithmetic or Boolean circuits to perform safe two-sided calculations. The previous method of using polynomials to approximate can work, but is too inefficient to use. So the authors propose to use such an activation function as an alternative. This function is used because, for one thing, it converts easily to 0 or 1 at the boundary and is very similar to the ReLU function for the other. And this activation function is circuit-friendly. It only contains a test if the input is in the interval minus 0.5, 0.5. The protocol is the linear part is still the same as linear regression, then switch to garbled circuit to evaluate this function, and then switch back. In privacy, preserving linear regression and logistic regression can both be smoothly intended to support the training of neural networks. They use the ReLU function as the activation function for each neuron and the cross entropy as the loss function. All functions in the feed-forward and feedback phases are simple linear operations, except for the summation and bias functions of the activation function. To sum and derive the ReLU functions, we simply convert to yaw sharing as we did for the logistic functions. The value and derivative functions of ReLU can be found together in one round, and the derivative results are used in the backfeed stage. They also propose an alternative to the safe multi-party computationally friendly softmax by summing all the outputs of ReLU and divide each output by the sum. In this way, the outputs are guaranteed to be probabilistically distributed. The main performance bottleneck is the offline phase, which contains a large number of cryptographic operations such as OT or HE, which of course will be slower than the simple add and multiply operations over a finite field in the online phase. So the authors had the idea of letting clients generate triples. Since clients need to share their data secretly in the first place, it is only natural to further let them share some additional triples secretly. Although the communication and storage overheads become larger, the online phase is still efficient because the offline phase is greatly enhanced. However, if a small group of clients and servers join together, they may be able to recover the coefficient of matrix, which harms the interests of honest clients. Therefore, servers and clients are not allowed to be in the same stream in this security model. Here is the results for 100,000 records and 500 features in each record. Offline phases in which triplets is generated takes around 400 seconds, and online phases is much faster. In one network, it takes around 9,000 seconds for offline phase and 141 seconds for online phase. If the triplet is generated by users, you can see that the offline time decreased significantly while the online time only increased a little. And we can get the similar result in logistic regression. Finally, neural networks. They implement the neural network in 2 hidden layers with 128 neurons each. It takes 25,000 seconds to train this neural network in a LAN setting, which had 35 times overhead compared to plain text training. In WAN, it performs even worse, which takes 220,000 seconds in total. This article analyzes the process of implementing linear regression, logistic regression, and neural networks for privacy preservation, specifically introducing these three techniques. However, we thought there exist some drawbacks. First, it is only applicable to shallow perceptrons or neural networks. How can it be extended to implement privacy-preserving deep neural networks while maintaining high computational efficiency? And second, the design of safe nonlinear functions is relatively simple. How to propose a perfect solution to the idea of sharing nonlinear functions? That's our presentation. Thank you for listening.
Thank you so much. Any questions? All right, so I guess, I mean, if you want to go to the next presentation as well, it will be too long. So my suggestion is that the presenters for the last presentation just be ready on Monday and then just present their work on Monday, if that's okay. Are you here? Let me see.
Yeah, we were here.
Okay, so is it okay if you present on Monday?
Oh, next Monday?
Yep.
Yeah, sure.
Okay, awesome. Thank you. So on Monday, what we're gonna do is like, we're gonna first, you guys gonna present, and then after that, I'm gonna continue the lecture. And from this point, we're gonna just, go back to the presentation. So let me share my screen. We can have like a 2-3 minutes of break, and then we can start the presentation, all right? Let me pause. So let's continue with the presentation. So we're gonna switch gears and talk about other stuffs in security. So it's kind of like, I posted a video over the weekend on the rest of the topics on privacy preserving machine learning. So if you go to the website, you can take a look at it and watch it. And then if you have any questions, let me know. Put it on the campus wire and we can discuss it. So today we want to switch gear and talk about other stuffs in security. And the first thing we need to do is kind of like, do some sort of like a back to the basics and talk a little bit about cryptography, because later on we're going to use it a lot. So it would be useful to actually get some idea about the cryptography. So I'm going to talk about, some fundamental concepts in cryptography that we're going to use later on in the course. All right. Okay. So, and then also I'm going to a little bit at the end talk about the class project as well. All right. So just to give you some overview, we're going to just go over the concepts. Most of the discussion would be non-formal, and we're not going to provide the proofs or theory behind it, unfortunately, because of course we don't have time. And usually cryptography itself is a self-contained course. So it's not like, 1 hour, 2 hours, or 1 lecture, 2 lecture would be enough for covering all these things. And the goal here is not really covering basics of cryptography. What we want to do is that we're going to use this in future when we are like talking about papers and other stuff. If you're really interested to know about cryptography more, my suggestion to you is looking at courses such as, CS 136 and 236, and then like, more advanced topics would be, of course, in CS282 series A and B. So if you're more interested in this kind of things, you probably have to go there or read some books, right? So the type of questions that we want to ask, and the reason that we need generally cryptography primitives are this type of questions. So for example, how to ensure that the communication are secure, right? This is like a very common thing that we usually need in our systems. So that's one of the basic questions that, like, how do we know that our systems are secure? The second thing is, how do we trust in each other's and different users, right? As we're going to show you in next few lectures, we're going to talk about Harvard trusted environments and Harvard remote computation and things like that. So what really we need to do is this fundamental concept of what is trust and how we can trust another user. And then finally, we also need a lot of, there are a lot of scenarios where we need to know, for example, whether a specific piece of record or data has been modified or not. So the information that we have received from potentially an untrusted, domain or user, how do we can actually get some guarantees that this data has not been modified, right? So kind of like an integrity management. To give you a little bit more formal definition of these questions, typically cryptography primitive is going to be used for ensuring confidentiality or privacy. So essentially knowing that, only the communicating parties in messaging, for example, know exactly what the message is and nobody else in between. It will be used for integrity, where guaranteeing that the message is either not compromised or not modified, or for using it for authentication and trust, where essentially we want to show or prove that either a specific identity of a person or user or a specific computation is either true, genuine, or valid. And we're going to talk about what is true, what is genuine, and what is valid. All right. So this is the kind of things that we kind of like need when we are talking about cryptography. And then cryptography, this is the tools that they will give us in our secure systems. Any questions so far? Okay. All right. So so the fundamental in most of these security systems is that we basically form some assumptions and definitions. Usually these assumptions are based off of some hard problems, some algorithmic hard problems that is proven to be hard. And then using these basic assumptions, then we kind of like, create our own statements based off these assignments and these assumptions. And we mathematically prove that starting from that basic assumption, this property that we want can be guaranteed, right? So this is usually the way that most of these cryptography primitives works. Of course, the challenges in such a behavior and approach is that, so first of all, the assumptions might be incorrect at some point. So there could be that we think that, okay, this specific problem is a hard problem, but it turns out to be that this is not a hard problem, right? So that's number one. The other issue is these assumptions may not be always correct. So for example, we are assuming that, breaking down a complex number to its own, the prime factoring problem is a hard problem. But as you know, probably that, for example, if quantum computing becomes a reality, then that problem is no longer a hard problem, right? So there are solutions for it once you have that ability. And it actually happens in the past as well. There were assumptions about certain cryptography primitives that once the computers become faster and faster, then they no longer become secure because the search space becomes much more faster and so on. So assumptions may not be always correct, unfortunately, and that's another key challenge that we're facing. And then the other two challenges that we're facing with cryptography is that, the implementation of that cryptography primitives can be buggy. So although in theory everything might works and we follow specific formal methods and mathematical assumptions and so on and show that indeed this system is secure, when we are actually implementing it in a real computer, at the end of the day it becomes a piece of software or a piece of hardware. And for the same reason that there might be bugs and issues in other codes, there might be bugs and issues in cryptography primitives as well. And in fact, history is full of these examples, unfortunately. So bugs itself can create lots of problems with this. And finally, as we're gonna extensively talk in this course, there's the issue of side channels. So we're gonna actually talk about side channels in about 2-3 weeks. But the idea here is that, we are assuming that, of course, each system has a specific set of, inputs and outputs. And then we are saying that, okay, this input is some sort of message and the output is some sort of ciphertext or information. And based off that, we are proving that the system is secure. But unfortunately, because this is actually the actual implementation, since it's actual hardware, there are some other activities going on in the system as well. So for example, the system can create some electromagnetic emanations, the temperature can goes up and down, and so on and so forth. So these physical activities or some sort of hardware activities of the system here can actually reveal some information from the internal values inside the systems, where when we were proving this system mathematically, we didn't think about those things. And actually, there are lots of clever techniques in order to extract this information and use. So as we're going to talk about, side channels information in future, we're going to see how this is going to be exploited and used, right? But for now, let's actually talk more mathematically and more theoretically and see why these systems are secure, at least on paper, all right? Any questions so far? Okay. So just to give you a very high level view of any crypto systems, typically a crypto system has 4 different parts. Usually there is the secret value, the secret information that exists in the system, and this is typically called key. This is the most important part of any crypto system. In some scenarios, there could be a key pair, or it could be even group of secret values. So it's not necessarily just one value. It could be multiple values together. We usually refer them all as the key. All right. Then there is the cryptography algorithms, which is the algorithm very deterministically say that, okay, this is the input, which is the message. This is the key. This is the secret value. You have to follow the specific steps that is very well defined. And at the end, you get some outputs, which is usually the ciphertext. Or if it's for example, decryption, it would be the message. Or if it's a hash, it would be a hash function, and so on and so forth. So what we are getting out of the systems, depending on what we are trying to achieve, would be that, right? So the inputs, usually we call it the message or code. And then the outputs, depending on what we are trying to achieve, could be the hash value, or could be the ciphertext, or could be message, and so on, right? So this is usually what the typical crypto system will look like. The very important things, I kind of also mentioned it at first week, is that it's very important for the crypto systems to be transparent, right? So this is based off this very well-known principle called Kirchhoff principle, Shannon principle, which essentially is saying that everything about a crypto system should be known except the key. So basically, if, for example, we are trying to hide a message, the only thing that should be hidden from the public world is, of course, the message and the key. And anything else about the system should be open public. So, for example, specifically what we should be very careful about is that we should not assume that the algorithm that we use in order to do the encryption or decryption or hash function or MAC or anything else is something that is obscure and secure and it's not known to the public. All right. So we can safely assume that all the algorithms that we use, everybody knows exactly all the steps through the algorithm. So in fact, actually all of these methodology that we are using in our computers, including AES or RSA and so on and so forth, all of them are actually public. You can actually look at the codes for all of them. You can download them and play with them and so on and so on. All right. So this is like a very, very important part of any crypto systems, that the algorithm itself should not be obscure. It should be public and known to everybody, including the attacker. Any questions here? All right. So the main two cryptographic modes is typically referred to as symmetric and asymmetric. The asymmetric one also sometimes called public key encryption or public key crypto systems. The difference between them is that in the symmetric key, crypto system, what happens is usually there is a shared secret between the two parties. So if we call it S, the S is shared between, for example, let's call it Alice and Bob. So the exact same value, exact same secret is shared between them. How do we share the secret between them? That's a separate story that we're gonna maybe talk about later in next lecture. But just assume that one way or another we managed to share this common secret between multiple parties. And then any sort of activity that needs to be done is going to be used with the exact same secret. All right. So for both, for example, encryption and decryption, if you want to do the encryption and decryption, both for encryption and decryption, we're going to use the exact same key. All right. In contrast, the asymmetric key is actually using a pair of keys, which usually called the public key and the private key. The names as suggest, the public key is actually something that is unique for a specific user, but is actually publicly shared with everybody. So, for example, I as a user, when I want to participate in a public key encryption mechanism, I'll usually create two pieces of information, one secret key and one private key and one public key. The private key is what I keep secret, so only I should have access to the secret key or the private key. And the public keys I'll just openly share with everybody in the board. So everybody should know what my public key is. And the idea here is that, as we're going to show you probably at the end of this lecture or maybe next lecture, for the encryption, we're going to use the public keys. So in other words, everybody can just, encrypt any message and send it to me. But for the decryption is actually where the secret key or private key is actually being used. And I'm the only one who can decrypt the message. So when we are actually going to talk about the asymmetric key, we're going to talk about this this information. So somebody asked, why does the use of a public key not expose important? Why does the use of a public key not expose important? Can you repeat the question? It doesn't make sense.
I could say the question. The question
Sure.
is, how come using a public key and having it be available, it's public, not allow malicious users to decode important data according to that public key?
So we're going to talk extensively about this, but the idea is that, for encrypting something, you use a public key. For decrypting the information, you use private key. All right. So in that case, just everybody can send you a message as much as they want, but nobody can actually decrypt the message that you have received, because you're the only one who has access to the secret information. All right. So sending a message is not an issue. Everybody can just send you a message. The key is that nobody should be able to decrypt the messages that you have received. Right.
I have a question too.
Yeah.
So just to make sure I got this correctly, the public key, it's like everyone in this Zoom chat room knows each other's Google password?
No. So your Google password, no. So your Google password has two pieces. One piece is shared with everybody. The other piece, which is the actual password, is only you know what it is.
Okay. Thank you.
I mean, once I start describing what asymmetric key and how public key encryption works, then you get more ideas. So it might sound a little bit unintuitive for now, but just hold on for a minute and we're going to talk more about it. Okay.
Okay, thank you.
Yep. All right, so now let's actually dive a little bit deeper and dive a little bit deeper and talk a little bit more about these things. So what we mainly going to talk about in this lecture is cryptography primitives. And primitives, there are usually different, there is really not a clean description of what is primitives, but you can technically think about it as just, the main building blocks in order to achieve specific security goal or task. All right. The popular ones is encryption, of course, encryption and decryption mechanism, either symmetric or asymmetric, secure hash function, message authentication codes, digital signatures, and so on and so forth. We're going to talk about most of these. In this lecture, I'm going to mainly focus on encryption and decryption and how it works. Hopefully in the next lecture, if you have some time, I'm going to talk about why these others are important. And in fact, actually, for the rest of this course, we're going to use a lot of these things here. So we're going to use a lot of hash function and so on in other things that we're going to talk about in this course. So that's why we need to know and understand what they are. But let's first actually focus on encryption and decryption. All right. There's also another notion called cryptography protocols. The protocols is actually, as the name suggests, some protocols, some algorithms that use this basic blocks in order to achieve something. So for example, we already talked about multi-party computation and secret sharing. If you remember last lecture, when I was describing this, I was telling you that you're going to encrypt something, send it to the other user going to decrypt something, do this, do that, and so on and so forth, right? I never actually described what the encryption and decryption algorithm works, but I just assumed that these are some basic blocks that we're going to use in order to achieve something that is bigger than that, which in that case was multi-party computation, where we want to jointly evaluate specific function without revealing our data, right? So there are lots of other things, including like zero knowledge proofs, login, key exchange, TLS, which works on top of the internet for all your messaging, blockchains, of course, and smart contracts is another big thing. So these are typically what is referred to as cryptographic protocols that use this basic blocks in order to build something. All right. And so that's usually the main use case of cryptography in general. We already talked about this. We're not going to probably talk about the rest of these things, maybe a little bit about blockchains if you have time, but the rest of it is probably, there's some other things that you will see in other courses as well. All right. So enough with the introduction. Let's actually now see how this, encryption and decryption works. As I said, we're going to focus mainly on that. So typically what happens is on encryption and decryption, we have a pair of algorithms in the encryption algorithm and decryption algorithm. Depending on whether we are using symmetric or asymmetric, the way it works is that we have some sort of message. We usually call it M. We either call it message or plain text. And then we have some key, which is the secret information that we have. And then the output of this encryption is this thing C, which we usually refer to as ciphertext. All right, so we call it ciphertext. Then for the decryption, the direction is opposite. So decryption algorithm takes the ciphertext and the key as the inputs and outputs the plain text or the message for us, all right? If this is a symmetric model, then both of these keys are exactly the same. If this is an asymmetric model, then this key would be public key, and this key would be a secret or private key, all right? Or sometimes we call it private. All right, so that's the general notion of encryption and decryption. There are two main properties that we are mainly interested in. The most important property of any encryption or decryption system is the correctness property. So this is like a must-have property for any sort of encryption decryption mechanism that we want to have. And that's basically says that if we encrypt the message and then decrypt it, we should obviously get the same message, right? So if you encrypt something and decrypt something and gets another message, this just fundamentally wrong, right? Because the goal is sending a message from point A to point B, and when it reaches to point B is actually going to be decrypted to another message, then the whole thing doesn't make any sense, right? So this is kind of like very intuitive and trivial, but it's actually something that's always has to be true. Another thing that kind of is also interesting to us is this notion of homomorphism, which, I mean, very general description of it is that if we encrypt some message, two different messages using same, of course, encryption algorithm, and we apply some function f on it, and if we decrypt this message after applying that function f, if it's equal to applying the function to the plain text to M1 and M2, if these two are equal, then we say that this encryption algorithm is homomorphic to a specific application. So for example, if F is addition, then we are going to say is homomorphically additive, right? If it's homomorphic to multiplication, we're going to say it's homomorphic to multiplication. If it's homomorphic to both of them, then we are in the realm of homomorphic encryption mechanisms, which can be used for privacy preserving and so on. The reason that I'm showing this here is that to tell you that not necessarily all the encryption mechanisms that we're going to talk about are actually have this property. Some of them may have this property, some of them may not have this property, some of them may have property over add, some of them may have this property over multiply, and so on and so forth. For homomorphic encryption mechanism that we discussed in the previous lecture, that's where we actually intentionally design an encryption system to have those properties, right? Otherwise, if you come up with a random, an arbitrary, homomorphic encryption mechanism does not necessarily have homomorphism. All right. So any questions so far? Okay, so from this point on, we want to talk about what is it that we make a specific algorithm, encryption algorithm secure, right? So at the end of the day, that's the major goal that we want you to achieve. And start with like a very basic question of what is a secure encryption algorithm? And here I want to pause and actually ask you this question. Intuitively, what do you think the answer to this question should be? So anybody, any suggestion?
So no one without a key should not decrypt the message and get access to the message in, I don't know, some sort of way.
Okay, so without a key, you should not be able to see the message. Somebody says Harper and Richard to decrypt, okay? The message cannot be leaked in any way without the key, okay? Yeah, so it's kind of like, you get the idea of generally what this is. So we are basically should say that, as you mentioned, it should be hard to completely determine M from C without the knowledge of K, right? So, and then this M, C, and K is the format that I use here, basically, right? So what we want to achieve is that it should be hard to completely determine, right? So here we might ask that whether it's possible to partially determine or not. That's a question that we're going to actually answer. But generally for a secure encryption algorithm, that's what we typically look for, right? But one question is that, is this basically enough? That this definition is correct enough and complete enough? And to understand that, let's actually look at the example here. But let's say we have only two messages, and if we are encrypting this, let's say we are encrypting one of these two just at random. What we are saying that for having a secure encryption algorithm, what is important for us is that there should be equal chance of after seeing C, there should be exactly equal chance of whether this C is actually coming because of M1 or M2, right? In other words, if there is not an equal chance, then the adversary can basically guess which of these two messages are the message that has been encrypted, all right? And what we really want is that typically we want to don't give any advantage to the adversary. What we want to do is that and any message that's coming, and so like any ciphertext that we are saying, there's an equal chance that is actually coming from the possible 2 messages that we can send. It could be bigger than that. It could be multiple messages. So what we want to do is that, for example, let's say if you have 4 different options, there should be equal chance of like 25% that seeing this specific ciphertext, the adversary can guess only by 1 over 4 at best which one is this. Somebody asked a question, how would the adversary know that the ciphertext C can come from these 2 or 4 messages? So just giving you an example, right? So let's say the adversary, so let's say somebody is sitting here and encrypting something and then sending out C. And then let's say the adversary actually sitting here and looking at this C that is coming from the system, right? So what we are saying is that seeing this C, so let's say C is basically, let's say it's like an 8-bit number. So it's like 11001100. What we are saying is that seeing this 11001100, the adversary should not be able to tell, okay, the chance that it's actually M1 should be higher than the chance that it's more than M2, right? So that's all we are trying to say, that it should be an exactly equal chance for all of them to be coming from the same scenario. Somebody ask a question? Yeah, raise a hand. Harry?
Hi, Professor. So I guess I'm reiterating the assumption, but similar to like hash functions, even in the case of encryption algorithms, we should make sure that like all the unique messages are like mapped to unique ciphertext. Like no 2 same messages. I mean, different keys shouldn't map it to same ciphertext for that sake. Like, is that the assumption that we made initially, or
No, this is not. No, this is not the assumption here. We are just saying that seeing a ciphertext should not reveal any information about the message. So the adversary should not be able to tell with some level of guarantee that, okay, the chance that this message is the original message is higher than that. So it's not just, we not be able to decrypt, but we also should not be able to guess which of these 2 are incorrect. So our best guess should be just random guess, right?
Okay, thank you.
Well, we're gonna get to that part of hash function, and what you're saying is collision resistance.
Yes.
And we're gonna talk about collision resistance as well in the future. All right. So the explanation that I gave you is what is called perfect secrecy. All right. So we are more formally, what we say, what is perfect secrecy is that if for all M0 and M1 messages in some domain M, so let's say we are doing messages from like all the different values between 0 to 1,000. So our M would be any integer value between 0 to 1,000. All right. And for all the ciphertext C that is in the ciphertext domain, so let's say our output algorithm is like a 10-bit value. So in this case, it would be between 0 to 1024. And for any random variable K that is uniformly distributed in some domain K, so our secret is also a value, right? So it could be like an 8-bit value. So what we're saying is that the K, the actual key that we're deriving from it is coming uniformly from that domain. So for example, if it's an 8-bit, the values should be uniformly from 0 to 255, right? So if you have this condition, then what we are saying is that in order to get perfect secrecy, the probability of encryption of message 0 using key K, which is equal to C, should be exactly equal to the probability of encrypting message 1, and that becomes C. So in other words, if you're seeing C, what we're saying is that it should be exactly equal probability if we had message 0 originally and encrypted and caused C, or exact same probability for the message 1. And we are saying that for all messages in our domain, this information should be hold true. All right. So in other words, again, back to the thing that I just said in the previous slides, that seeing C, there shouldn't be any difference between M0, M1, or any other messages in our systems. All right. So is that clear what perfect secrecy is? Anybody has any questions? So that's what we're getting from perfect secrecy. And then the obvious question is, okay, can we actually achieve perfect secrecy? And the answer is yes, actually. And the way that we can achieve perfect secrecy is quite simple, very surprisingly. And actually, there's this notion that's called one-time pad or OTP, which is basically a very simple thing. It just says that, K is the secret. All you need to do is that take the message and XOR it with the key, and that would be your ciphertext, all right? So one-time pad is just this very simple function. There's nothing but an XOR. And what it does is just XORing whatever message that you have, XOR it with the key, and then that would be your ciphertext, all right? And there's actually an extensive mathematical proof that shows that this indeed satisfies this requirement that we are showing here. So for all the messages, as long as this K is actually uniformly distributed over the domain K, then this information is correct. All right. So then we're gonna achieve perfect secrecy pretty easily. So our encryption and decryption mechanism in OTP is quite simple. If you have a message, M and we have a key K, what we do is that we just, XOR, bitwise XOR these two together. And we're gonna get our ciphertext C. And then the interesting thing is that decryption is actually the exact same thing. The difference is that, I do decryption of C with K, and what I'm gonna get is M. And you can actually test it for yourself, because if you XOR two things twice, you will get the original value itself as well. All right. So it actually it satisfies the correctness issue that we wanted to have as well, and it's very simple as well, and it's also achieved perfect secrecy. So both of the things that we want to have, we can achieve with this. Any questions so far? Us. So far so good, but unfortunately there is issues with one-time pad, as you would expect. And the major issue is that in order to achieve perfect secrecy, the key size and the message size should be exactly the same, right? So if you think that why this would be an issue is because of the practical issues, right? So imagine that we have like a 1 megabyte of file in our computer, and we want to encrypt this 1 megabyte of file. It means that we need a secret key that is also 1 megabyte long, right? And then essentially what it says is that, for whatever message that you want to encrypt, you should store the same amount of key, which means that the overhead would be double. And the bigger problem is that, where you're going to store this secret key, right? Because storing this secret key has lots of challenges. It doesn't have to be, available to the attacker and so on and so forth. And remember, when we are using, symmetric encryption, this secret key has to be shared between both sender and receiver. So what we need to do is that sharing this 1 megabyte of data with the receiver as well, which is also another challenge, right? So having the same size of key and message, unfortunately, is actually it's not feasible at all, right? There are lots of issues with this, and it's not doable to achieve something like that, right? Any questions here? Any doubts of why having the same size key is an issue? Okay, Shreyas?
Yeah, perfect. I just want to reiterate just to make sure my understanding is correct. The key will be changing based on how you draw it from the distribution, right? And it's also assumed that the different keys are known by both the person who's sending the message as well as the receiver.
So we can assume that it would be a one-time thing. So we draw it from the distribution one time, we get a key K, and then we're going to share it to, let's say, Alice and Bob, and then start the encryption process after that.
Okay, so in that case, if the message is only like, for example, a yes or a no, wouldn't the encrypted message always be the same and wouldn't like the adversary be able to figure it out?
if you so we are talking about one-time pad, right? So for now we just encrypt things one time. All right. So if you have a message yes or no, right? So let's say this is 0, this is 1, and our key, let's say, has to be also 0 or 1, right? So what happens is that there's an equal chance that whether we pick this key or that key, right? And then if we pick this key and let's say our answer is yes, the XOR of 0, 0 versus the XOR of 0 and 1, right? So the XOR of 0, 0 would be 0, the XOR of 0, 1 would be 1. So what the adversary will see, it depends on which key we have used. And since we completely randomly select which key, there's an equal chance of being 0 or 1 what the adversary sees. So the adversary guess is nothing less than 50%. But you're right. If we keep repeating it, then there will be problems, and we're going to actually talk about that. But we are talking about one-time pad, which means that we are just doing this thing one time. And that becomes many-time pad, then it has its own issues that we're going to talk about.
Okay, thank you.
Yep. All right. Okay, so what should we do? And the answer to that is we need to kind of relax the perfect secrecy. So unfortunately, there are mathematical methods that shows that in order to achieve perfect secrecy, you have no option but having the same size for the key and the message, all right? So there is no way of achieving perfect secrecy in another way, all right? So what we need to do is kind of relaxing perfect secrecy. And in order to do that, we are defining another notion of security, and we call that semantic security, right? So the semantic security is basically kind of similar to what perfect secrecy is, but instead of saying that, you know, the probability that we are seeing C and that becomes from M0 or M1 should be exactly the same, we're saying that it should be negligible. So it should be essentially more mathematically, if I want to show it, it should be the probability of C, you know, C is equal to the encryption of message 0 minus the probability of C is equal to encryption of message 1 should be less than something called epsilon, which is some sort of threshold that we can define. All right, so that's what the semantic security is going to give us. And two questions coming from this. The first question is, okay, how much is negligible? And that's really depends on the systems. So usually these days, for example, the keys are being like 128 bits and so on. So think about like numbers in the order of minus 128 or so, right? This is the negligible amount that we're saying, but I mean, there's no you know, well-defined answers. It really depends on the speed of the computers, the efficiency of the computers, and so on. But these days, like, you know, the negligible number should be something around this number, all right? And the second question is that, okay, how does this help with the OTP? Later on, we're going to show that this is going to help us with relaxing this issue of, you know, the size of the key should be equal to the size of the message. In fact, what we're going to show is that semantic security is going to give us this option that, you know, the size of the key can be actually much, much smaller than the size of the actual message. And that's good. That's what we want, right? So that we want to like use, for example, a 128-bit key and use that to like, you know, encrypt 1 megabytes of message. That's ideally what we want. And as we will show in the next few slides, semantic security is going to give us that. All right. So any questions here? All right. So to give you a little bit more context about semantic security and how does it work, let me introduce this thing called the attack game. So actually, this is going to be used a lot in many of proofs for lots of these different, you know, theorems and lemmas in cryptography. So I thought that it would be useful to describe what the attack game is and then use this for the semantic security as well. So in the attack game that's going to be used a lot in cryptography, you will usually see two players, which they usually call it the challenger and the attacker. right? There are lots of rules in the game, and the main things are that the challenges usually follows a very simple fixed protocols, which in most cases, for example, it would be some encryption algorithm. The attacker, although we can assume that the attacker follows any arbitrary protocol, so it doesn't necessarily have to follow the encryption protocols. It can just follow anything that he wants or she wants. But what is important is that we still assume that the algorithm that the attacker runs is an efficient algorithm, is an algorithm that is doable in polynomial time. So it's still in P, right? So it can be done in polynomial time because we are assuming about normal computers with normal powers. All right. What happens is that during these games, the player is gonna send and receive some messages and some information to each other. And at the end of the game, what happens is that the attacker gonna make some prediction. So gonna output some values we usually call prediction. And depending on the scenario of the game, which as we're going to talk more about it in the next few slides, what we want is that this prediction usually should be smaller than some threshold value, right? Or it should be equal to random guessing, all right? So what we want in order to prove a security of something is that during these games, once the attacker make the prediction, that prediction should be close to just some random looking prediction, all right? So using this concept in semantic security game, basically what I just described in 2 slides ago, we're going to have a challenger and the attacker A. And what happens is we are assuming that, for example, we have 2 sets of experiments. We call it experiment 0 and experiment 1. So B could be either equal to 0 or it could be equal to 1. So what happens is that the adversary first pick 2 messages at his own choice, and the message is coming from the domain M. So let's say, for example, it's 8-bit values. Select 2 8-bit values. It could be at random. It could be at any strategy that A wants. We don't care. Then what happens is that the challenger then is going to create a key. It's going to randomly select it from some distribution K. And then it's also going to encrypt the message with that value that it has. So it's going to either select 0 or 1, right? And it's going to encrypt that message, and it's going to send C to the output, back to the attacker, right? So either pick M0 or M1, encrypt the message, and send C. Then the attacker can use any algorithm that he wants. And basically what it does is that at the end of the day, it's going to send out 1 bit of information, which we call the B hat. And that B hat could be either 0 or it could be 1, right? So just make a prediction. And what we are saying is that this encryption system, this E, is semantically secure if the probability of the attacker correctly detecting this is just random. So it's basically just 50% plus some epsilon. All right. So that's all we are saying by semantic security. So basically the attacker can choose any messages that he wants. He can play with, he can run any test that he wants on C. At the end of the day, after some time, is going to make a prediction. And what we're saying is that the probability of making that prediction should be not by a significant amount better than 50%. All right. So that's all about semantic security in the context of this security game. Any questions here? All right. So we don't have much time left. So what I'm going to do is that I'm going to just continue this in the next lecture. I'll record a short video and send it to you. And then after that, we're going to continue most of these things on Monday. All right. So, and then for the projects, those of you who wants to talk with me, either today, you can stick around after the class, or I'll probably send out an email and set up some sort of an office hour either on Monday or on Friday these weeks to talk about the project as well. All right. So if there's no more questions, you can leave. Let me actually pause the recording. And those of you who have questions or want to talk about your projects, you can stick around a little bit. All right. Thank you.